All right, let's begin this example. In this one, we're told we have air expanding isothermally at steady state with no internal irreversibilities through a turbine from one pressure and 500 Kelvin to another pressure, a lower pressure. We're asked to determine the heat transfer per unit mass flow rate of the air and the work per unit mass flow rate of the air. So let's go ahead and sketch out what this situation looks like. We have our turbine, and we're told we have some flow coming in, going out. This is our turbine, and there's some work output as well. We're also told that there's some heat transfer. So normally we say that flow through the turbine is adiabatic, but here we're told to don't make that assumption. Instead, what we want to do is we want to calculate what the heat transfer is for this particular case. So I'm going to go ahead, put in some heat transfer, and I'm going to make the turbine my control volume. So I'll put a dashed line just so everybody knows what control volume it is I'm working on. And we're asked to find initially the heat transfer per unit mass flow rate for a case where we have no internal irreversibilities. So I'm going to use the entropy equation to find that. If I use the first law, the problem is I don't know the work either. So in the first law, I would have two unknowns. I wouldn't know the heat transfer, and I also wouldn't know the power. So that's why I'm going to use the second law, or the entropy equation instead, because there that involves heat transfer, and I'm also told some information about the internal irreversibilities. So let's go ahead and write out the entropy equation for that particular control volume. And it'll be the rate form, since I'm doing everything as, you know, there's a mass flow rate going in and a mass flow rate going out. Everything's in terms of a rate. Okay, so here is our entropy equation for that control volume. Let's go ahead and simplify things. First of all, the time rate of change of entropy within the control volume is going to be 0 because we're going to assume that this is a steady state flow. We're at steady state conditions that if you took a picture of the situation now and you compared it with a picture sometime later, the two pictures would look the same. There's no accumulation of entropy or any reduction in entropy within the turbine itself. Okay, so we have that one. We have the mass flow rate coming in. There's only one inlet and one outlet, so the mass flow rate coming in will be m dot S1. Going out will be m dot S2. And just note, from conservation of mass applied to the same control volume, go ahead and write that out as well. From conservation of mass on the same control volume, the left-hand side is 0 because it's steady state again. We have one inlet, one outlet, so what you'll get is m dot 1 is equal to m dot 2, and I'll just call it m dot. Okay, so it's the same m dot at the inlet and the outlet. We're told that there are no internal irreversibilities, so it means it's reversible. So that means the s dot is 0. So it's internally reversible. That's given in the problem statement. So then we can go ahead and just simplify this equation. So let me go ahead and do that, and I'll bring the heat transfer term to the left-hand side. So let me just write this out. So if I bring that to the left side, that'll be negative. So it should be m dot S2 minus S1. All right, so then and there should be a q dot there. So let me go ahead and rearrange things just a little bit more. I'm going to divide through by the m dot because we don't know the mass flow rate, and we're asked to find what the heat transfer per unit mass flow rate is. So that's why I've done some rearranging there. All right, so now I need to figure out what each of those terms corresponds to. For the temperature, we're told that the process is occurring isothermally and at 500 K, so we're going to assume that that's the temperature right at the boundary here. Okay, so I'll make a note of that, where T is equal to 500 Kelvin. And then to find the S2 minus S1, what I'm going to do is assume that the air, since we're dealing with air here, is an ideal gas. So we'll use our ideal gas model to figure out S2 minus S1. So when we write that out, it'll look like the following for an ideal gas. So the assumption here is assuming air is an ideal gas. Okay, now what we need to do is figure out what the S0 values are. Those come from, well, first of all, what we see is that they're a function of normally those would come from the ideal gas table, but if you notice that these are functions only of the temperature, which means that if the temperature doesn't change, because this is considered an isothermal process for this problem, those two will cancel one another out. So I can write out S0 T2 is equal to S0 T1 since isothermal. So those we don't have to factor in. So then our S2 minus S1 will be minus R, the gas constant for air, times the natural log of P2 over P1. And we know the values for those. So where R for the air is 0.287 kilojoules per kilogram Kelvin. P2 is given in the problem statement as 2 bar absolute, and P1 is given as 10 bar absolute. So we can then evaluate those numbers as well. So when you start plugging in the values, you'll get delta S here, comes out to be 0.46191. It's a 9. Let me erase that and try again. So delta S is equal to 0.46191 kilojoules per kilogram Kelvin. And then the Q dot into over M dot comes out to be 231 kilojoules per Kelvin. All right, so that's the very first part of the problem. Let's go back up to the problem statement again. So what we've done is we found the heat transfer for this particular case, making use of the entropy equation and knowing that it's internally reversible. And we also assume that since we're dealing with air, we're dealing with an ideal gas. We did not make a perfect gas assumption. Rather, we just used an ideal gas. So anyway, we didn't have to make a perfect gas assumption for that. The next part of the problem is to find the work per unit mass flow rate of air. Here we can go ahead and use the first law applied to the same control volume. So let's write that out. So the first law. The reason I want to use the first law is because that involves the heat transfer as well as the work. So we'll go ahead and write that out. Okay, so we now have our first law expression. Again, the time rate of change term is 0 because it's steady state. There's the total energy within our control volume does not change with time. We're going to neglect kinetic and potential energy effects. We're not told anything specific about them in the problem statement, but typically those are small in comparison to the other terms in the equation. And we've already said something about the mass flow rates, so we won't. We know that m dot in is equal to m dot out. So let me go ahead and solve for the work that we get out of the control volume. So that'll be q dot into plus m dot h1 minus h2. All right, well, we just solved for q dot into, so we know that value. The H1 minus H2, again, we can go back to our ideal gas model, and what you'll know from the ideal gas model is H is just a function of temperature. It's only a function of temperature for the ideal gas model. So since we're dealing with an isothermal process, H1, which is at T1, will equal to H2, which is at T2, since T2 is equal to T1, because it's isothermal. So the specific enthalpies will cancel out. So then what we're left with, if I divide through by the mass flow rates to give me the power per unit mass flow rate, you'll see that the power per unit mass flow rate is just the same as the heat transfer per unit mass flow rate. So they just come out to be the same value. All right, so that's all there is to this example. Again, just to kind of recap, what we did is we started with the entropy equation in order to find the heat transfer, because the entropy equation involves heat transfer, and since we're not given the work done, we didn't want to use the first law because that would give us another unknown in the first law. So we stuck with the entropy equation. We were told that we're dealing with an internally reversible process, and we were able to make use of the ideal gas model in order to figure out what the change in the specific entropy was. And then to find the work, that's when we used the first law because it involves the work term. We had already just solved for the heat transfer. We were able to neglect the specific enthalpies because we know that for an ideal gas, it's only the specific enthalpy is only a function of temperature, and since the temperature isn't changing, it's an isothermal process for this particular case, those specific enthalpies crossed out. And so then we were left with the power equaling the heat transfer.